Uh, can you hear me clearly? Can somebody hear me clearly? Can somebody hear me clearly? Okay, good morning, everyone. And I want to welcome you to another statistical learning class. Today, got two materials that I'm gonna walk you through. Give me 1 second. Okay, so I think I need to have a kind of recap, coming into this topic. We've done different types of regression models. Okay, so what I'm going to do before going into multinomial regression model is to tell you that what determines the choice of regression model at times depends on the nature of the response variable. So when response variable is continuous, I'm going to say that again. If response variable is continuous, and our intention is to investigate relationship between variables or to make a prediction of the response, of course, we're going to use normal linear regression. When the response variable is categorical in a way that it has two levels, we're going to use binary logistic regression. But what if in a situation where the response variable is neither continuous nor categorical? If it is a count, then we make use of Poisson regression model. Now, what if in a situation? So what we want to do today, the two type of regression model we want to do today, okay, they are related. And I'm actually going to say the two of them are generalization of binary logistic regression. I'm going to say that again. The two type, regression models we want to talk about today, they are generalization of binary logistic regression model. In a binary logistic regression model, we got two levels. But in a multinomial regression that I want to talk about, if you see multinomial, it means we got more than two levels. The response variable is categorical here, but we got more than two levels. When we got more than two levels and they are not ordered, I'm going to say that again. If there's no any ordering, okay, for instance, maybe I'm talking about race, or I'm talking about state, or I'm talking about colors, okay, in that kind of situation, they are not ordered, okay, without, and they have more than two categories. I'm actually going to use multinomial logistic regression. But what if in a situation where I got more than two levels and they are ordered, okay, and they are ordered. Example, you talk about somebody winning you know, three type of whether a gold medal or silver medal or bronze medal in Olympics. Everybody knows the worth of gold is bigger than the worth of silver. in that kind of situation, okay, the response variable is winning gold, okay, of course, you're actually going to use ordinal or logic or proportional logistic regression. But situation where there's no ordering is going to be multinomial. So the two type regression model we want to talk about today, the two of them generalize to more than, generalize the situation with two levels. So they have more than two levels. I want to welcome you to multinomial. Of course, in the binary logistic regression, the underlying distribution was binomial because we use binomial to model events with two possible outcomes. And that was why the underlying probability distribution was binomial. But situation where there are more than two possible outcomes, we should be talking about multinomial distribution. So when I present to you, take a look at it. That's a multinomial distribution. Okay, this is a probability mass function of multinomial distribution. For binomial, you got two levels, two possible outcomes. For multinomial, here I'm trying to say k possible outcome. And that very k possible outcome will mean k categories. Okay, now the interest is actually to have a way to investigate individual in a particular category. If you take a look at what I have here, I said this guy, for each group or individual high, okay, the YIK represent the number of observations falling into K category. Don't forget, I is an individual. Okay, when I say YIK, I mean individual I falling into category K. Does that make sense? That's exactly what I mean. And of course, we are interested in figuring out the number of such individual. Take a look at this. NI equals summation YIK is like you are summing individual falling into that category. If you take a look at that, you can say NI equal to that. And the PIK is the probability associated with that random variable individual. But you know what? The sum of probability, okay, the probability of falling into a group, the sum of that has to be equal to 1. That's what I mean here. Okay? So I need you to pay attention to this. I said for each individual or group or individual I, so I is for individual, K is for the group, the category the individual belong. Okay, and I said NI equal to this. Okay, what are you summing here? You're actually summing that a particular across the numbers of groups. That's exactly what you're summing here. And this is the probability associated with that. And this is to tell you the sum of that has to be equal to 1. Okay? Now, situation where we have on group data, the NI is going to be equal to 1 because here, idea of grouping will take a center stage. I'm going to say that again. The idea of grouping individuals into different categories take a center stage. Okay, but for on group data, we expect NI to be equal to 1. Okay, now that is that. Now I'm actually going to move to the model aspects, and I need you to pay attention. Now we all know that the sum of probability has to be equal to 1. The probability of individual B in whatever group, when I had help, that's going to be 1. That's why you see summation PIK equal to 1. Okay, but before we proceed, there's something that we need to do. We got K number of categories. We need to be able to decide among the K levels, which one are we going to reference? Okay, which one are we going to nested? That's going to be nested in the intercept. Okay, we need to decide on that. And that was why I said typically the first one or the last one, we can set k to be equal to 1, and that k equal to 1 to be a baseline, for instance. We need to have a baseline because that will give us an opportunity to compare for comparison. If we choose a baseline, that will enable us to make a comparison between the level of categorical variable and the one that you reference. And because of that, when set k to be 1 as a baseline instant, then the pi, the probability now become 1 minus. I need you to pay attention to this guy. Give me 1 second. I'm going to pay attention to this. You're actually going to see k start from what? 2. Because I've already referenced one level of categories. Okay, now how does the multinomial logistic model work? How is it different? Is it different from binary logistic? The binary logistic, the logit is log of pi divided by 1 minus pi. But here, log of pi divided by 1 minus pi is like we are only considering 2 categories, because the first pi is a probability of the characteristics of interest, that of the presence of the characteristics of interest. 1 minus pi is a probability of the absence. That's our 2 categories. But here in the multinomial, we're going to have so many categories. But what we're going to do, we need to, for of us, have a reference. If you take a look at this, I have a log of pik divided by pi1. The one that I reference is the one that will be in the denominator. I'm going to say that again. The group, the category that was referenced will be in the denominator. Then I'm now going to look at the one in the denominator will be the order level with the respect to the one that I've referenced. And I'm going to equate all of that to systematic parts. This is a systematic part, but when you take a look at the systematic part, all of them, the beta null, the beta j as a k, because we are actually going to compare one category at a time with the one that is referenced. One category at a time with the one that is referenced. That is what that is talking about. And of course, our k will start from 2, because what you have in the denominator is for k equal to 1. That is the one you reference. Okay? Now, if this is in the log form, we can also have in a probability form. You remember in the logistic regression, we got 2 forms of that, right? Logit form, where you have the log of odd equal to the systematic part. And we also have the probability form, where you have a pi cap, right? Equal, something. And you derive the pi cap, you solve for pi cap from the logit form. We're also going to have the same here. Okay, this is the PIK. I may really want to estimate the probability, this is like, can I estimate the probability that certain individuals will fall into a particular category, putting into consideration predators? I'm going to say that again. Can we have a way to classify, individuals into a particular category using the information available about the explanatory variable? So that's exactly what I mean. But for you to really understand, so like I said, this is the model. This is the log form of the model, and this is the probability form of the model that you need for prediction. Of course, we use all this for this is a classification problem, okay, where we want to classify into so many categories, more than 2. I'm going to go into example. We have data set in R that we're actually going to use. Okay, we'll consider the NEST 96 data set from our package far away. And of course, the data set collect the voting preference and characteristics of 944 people collected in the following variables. You have a population, TV news, and so on like that. Now, this is looking like a political data. We got a lot of variables. Okay. But and now party affiliation. Okay. Party affiliation is what we're interested in as a response. In the party affiliation, we actually want to consider three major political parties in the United States. Okay, the Republican, the Democrat, and the Independent. Of course, the idea of a multinomial logistic regression is going to work here because those parties are not ordered, but they are more than two. And of course, these are several other predators: age, education, income, and so on like that. And when it's like we want to have interest in testing the effect of income on the party affiliation. And if you take a look at the respondent family income here, okay, 3K, less than 3K, less than 3K to 5K, 5K to 7K, these are being categorized, but the lowest category here is 3K to 5K. That is the lowest category. And don't forget, when you are working with a multinomial logistic regression, we need we need to have a kind of reference. Now, take a look at this. I actually want to load I want to start, I want to prepare for analysis right now. Okay, and I'm actually going to curate a levels among the SPD or SPID, the categorical levels, the Democrat, the Republican, and the like. I talk about party affiliation. And of course, I want to look at the effects of income. But what I want to do is probably to make our income numeric, because initially the income was categorical. But I'm going to show you uh, how to mode. Now, I need you to pay attention. When we're fitting linear regression, it was LM. When we're fitting logistic regression, fitting Poisson regression, we write GLM. So what distinguishes between Poisson regression and logistic regression is just family that we normally indicate. In Poisson regression, family equal Poisson. In the binary logistic regression, family equal binomial. But I need you to pay attention now for multinomial. For multinomial, is actually going to be multinom. Do you see that? Multinom. Okay, multinom. The response variable is categorical SPID. It must more than two levels. And I'm only looking at the effect of income on that. I want to look at the effect of income on party affiliation. Okay, the effect of family income. And initially the income was actually INCOME. The income given here is categorical. They have to change that to numerical. So that is exactly what we're trying to do, here. Okay. And right now, let's look at the results. Okay. Now in the results, I need you to pay attention. Please pay attention. Something crucial. Pay attention. In my results, I only saw this. I only saw independent and Republican, despite the fact that we have three political affiliation that we consider. But let me tell you this, we've done something here. We've actually done something here. Can you see the here? We actually want make whether you are the one, you can decide to choose whatever level as a reference. But if R choose that for you, then let's say I didn't choose anything and R will run that, and I run that in R, and I only have this, then it means R has automatically referenced the Democrats. Does that make sense? You can decide yourself to reference a particular level. Okay. Now, if R has automatically referenced Democrat, that's why you see in the output independent and Republican. Okay. Now, the result is going to come in two ways. The output is going to come in two ways. I need you to pay attention. It's going to come in terms of coefficient, also going to come in terms of standard error. Can you see that? Standard error. It's going to come in terms of coefficient. It's going to come in terms of standard error. Now, you know what I want us to do now? I'm actually going to have two models, two separate models. I'm going to have one based on independent, and I'm going to look at that independent relative to the one that was nested in the intercept, the one that was referenced. I'm going to look at independent relative to Democrats. I'm going to look at Republican relative to Democrats. Because of that, I'm having two models. Does that make sense? Is there any question here? Now, there's something I actually want you to see. Okay, if I'm going to start the first model, independent relative to Democrats, log, you have to write a log, P of independent into that. Then here, it's just going to be the systematic part. The systematic part is always going to be a linear. Whether you're talking about Poisson regression, you're talking about logistic regression, you're talking about multinomial, the systematic part is always going to be a linear combination of the predictor and the regression coefficient. Okay, now these are the two models that I'm actually going to have. Right now, what is my beta 02? Okay, my beta 02 is negative 1.174931. Then the beta 21, of course, is actually going to be that for income. Okay, now when you go to the Republican aspects, it's going to be that for that, and that is going to be that for that. Okay, now which means beta 01 is not captured. The beta 01 represents the intercept for the Democrat that was nested in the intercept. Does that make sense? Okay, now this is the estimated model. I'm seeing a lot of midterm 2 questions because what I'm going to do in the midterm 2 question this time around, you are not going to do anything necessary in R. I'm going to provide the outputs. The midterm 2 will test your knowledge of interpretation of output, of our output, okay, or your computation. Calculator is going to be enough for that exam. But I needed to pay attention. Now, this is the model, okay? Based on that, is there any question on this model? Any question? Okay, now without question, I'm going to move. What if I ask you, what is the standard error of that? What is the standard error of that? You actually need to come to the standard error section. Okay, you can see this guy, the standard error of BO2. Okay, the standard error of BO1 is not listed because that level category is what is nested. What is reference? Okay, so take a look at that. Now, can we have a kind of question on this? Now, if the question asks you, can you provide an interpretation for the slopes? When I say for the slopes, please pay attention for the slopes. They're going to be, we have two types of slopes here. The one for independent, the one for the Republican. For the slopes. One for the independent, one for the Republican. Now, for instance, if I actually want to make an interpretation for this guy for the independent, because I'm dealing with the log. Okay, don't forget what I have here is a log hard estimate. Because I'm dealing with a log, okay, it's a log estimate that I'm actually going to do exponentiation. Can you see that? I have to do exponentiation. We also do that in logistic. We did that in logistic regression on Wednesday. Now I'm going to exponentiate. I'm exponentiating the one for independent right now. Okay, the slope for independent. I'm also going to do the same for the Republican. But how am I going to interpret that? This is what I got. So I'm going to say when the income increases from one level, okay, the odds, please pay attention. You always, whenever you have exponentiated, you don't talk about log anymore, but we talk about odd. because the log of odd, exponentiation of the log of odd is going to give you odds. Because I'm going to write this right now. So the exponentiation of a natural log of a function is going to be a function. So when I have a log of odd, and when I exponentiate that, it's going to give me odd. And that is the reason this value now, that's how it is interpreted. Now, right now, I said when the income increases of one level, the odds of being an independent rather than a Democrat increases of that. Why do I mention increases? I mention increases. I need a sign of that particular beta. So what I'm actually going to do, I'm going to come back here. How do I know it increases? Okay, I'm actually coming here. Can you see it's positive? Okay, that's why I say increases. If it is negative, I'm going to say decreases. I'm going to do the same for Republican. When I do the same for Republican, it's going to be, you're going to compare that to the one that you level your reference. Is there any question here? Is there any question here? Now I said, so which means you actually, when I say you should interpret the slopes, I only interpreted one, right? This is incomplete. Look at that. Slopes. You have more than one slope. So it is expected that you interpret it two. You exponentiate it two. Okay? Not just one, except if the question is specific. Does that make sense? Okay. Now, I said something here. Since the regression parameters correspond to the log of the odds. Now, I need you to pay attention. It may not be easy to interpret. That is why we may not be able to interpret this directly. Okay? We can't interpret that directly the way it is, because the way it is right here, it is a log odd estimate. So log odd estimate is very difficult to interpret, and that is the reason why we need to exponentiate that before interpretation. Okay. Now, the next thing we can do is, do you know, knowing the income, can we have a way to make a prediction? What would be the probability that will be in each level? What is the probability that will be Democrat? What will be probability that will be Republican? What will be probability that will be independent? If I actually know the level. So which means what I actually want to use, I'm actually want to come back into the formula here that I talk about. This guy, can you see this? This is what I want to use. I want to have an estimated, estimated probability. I want to have an estimated probability. Okay. Well, at least I want to, knowing the value of a predator. Don't forget, I already have my feeder module. Okay. It's more or less like if I have my feeder module that is in the logit form, I can solve for pi, solving for a pi curve. That's exactly what I need to do. But you know what? We got a code in R that you can actually use for that. Okay, we got a code in R that can be used for that. Now, I need you to pay attention. Okay, I said it is suggested to compute the predicted probability for fixed values of the covariates. Covariates here is the income. If I know the value of income, can I use my model to predict individuals? What will be the percentage of Democrat? What would be the percentage of independent? What would be the percentage of Republican? It's more or less like if I meet a politician in the United States that is classified as a Democrat, Independent, or Republican without knowing his party's or a party affiliation, can I use the family income to predict the class? Whatever would be his party affiliation. That is exactly what we want to do here. Now you're going to use a predict function now. MMOD, don't forget that's what you use to fit your model. MMOD, can you see that? MMOD. Okay. Now when you do predict, now data frame, you now need to suggest a value for the income. Here I said equal to 1 because when you go back to the income that we have, the lowest one is the lowest category is 3K to 5,000. Okay, so we can circle that one. Now, for whatever values of income, now right now, after saying that, then you're gonna say type equal props. Then this is gonna give you this. Now, can you see that now? Okay. Now you'll be able to know the percentage in each category. That is exactly what you have. Now, can we provide an interpretation for what we have right now? Please pay attention. How do we provide interpretation for that? Okay, we actually, I said the other time, less than 3,000, that category is actually income one, it's seen as income one. And I said, if the yearly income is that, then the probability to be a Democrat is actually to 2 decimal is 0.59. Can you see that? And the probability to be independent, can you see that? 0.18, and to be Republican is that. That's what we mean. So that's how we interpret that. Now, that is going to be the end of the multinomial. Like I said, we're using multinomial when we have the response variable is categorical and it has more than 2 levels, and the levels are not ordered. But what if in a situation where the levels are ordered, you want to answer a question where maybe you want to know what determine customer satisfaction, and where you have very satisfy, not satisfy, and so on like that. Those are ordered. Okay, those are ordered. There are more than 2 levels. Of course, you can't use multinomial for that regard. And that is going to take us to another. Okay, that's going to take us here. I want to welcome you to logic proportional odd models. Logic proportional odd models, we're still talking about more than 2 categories, more than 2 levels, but this time around the levels are ordered. Okay, the levels are ordered, and that was why I said when fitting logic multinomial models for ordinary variables, we are essentially throwing away the information regarding the ordering. Okay, we're throwing away the information regarding the ordering because the level of the categorical variables are not ordered in that regard. They are, multinomial logistic regression is going to be appropriate for that kind of situation. But what of in a situation where the levels are ordered? And that's what I said. An alternative regression model which does account for the order across the categories is what we want to talk about right now, that we call the proportional odd model. I want to welcome you to proportional odd model. Okay. Now you know the difference. Okay. Now I want to also talk a little bit about what the example is going to be, the model architecture, and the statistical framework. We're actually going to have a gamma I k, and because ordering is involved, inequality is going to come in. Inequality is going to come in. There's a difference between equation and inequality equation. Whenever there is, when you are using equality, you're more or less trying to say, oh, the levels are, there's no level that is more than the other. But with the inequality, then you're trying to say a particular level is actually more than the other. And that's why you're gonna see us using this probability of a yi less or equal to k. For instance, so what does that mean? If I have four levels of response variable, maybe a position in an organization, the blue collar, the white collar, the managers, and the CEOs. Take a look at that. Okay, there's a difference in this. Uh, now there's a kind of ordering here. Okay, and I want to interpret gamma 3 high. Okay, K equal to 1 is blue colors, K equal to 2 is white color, K equal to 3 is managers, and K equal to 4 is going to be that. But you know what? If I want to find, I say probability of yi less or equal to K, less or equal to means at most, right? At most. Okay, and that was why I said here, I want to find what is the probability that individual I works in a position not higher than managerial. Not higher than is at most managerial. It's either is in it works in the position of managerial or what or less. Does that make sense? That's exactly what I mean here. Okay. So now based on that, if you take a look at this, I've introduced ordering. Okay. In the multinomial, there was nothing like ordering. Take a look at that. I will end up, category 1 less or equal to category 2, and so on like that. It means the biggest one is going to be category K. Does that make sense? Okay, now, if that is what we have, okay, how do we write the model? And let me tell you this. Just like what we have in the multinomial, where we actually only out of 3 levels, the arrow report 2 levels. Arrow report 2 levels because we don't want to fall into a dummy variable trap. We're also going to do the same thing here. Okay, now we're going to write logic. Now I'm showing you the model now. Okay, I'm showing you the model, the proportional odd models used in a situation where there is ordering. Okay, now take a look at this guy now. Logic gamma high k equal the log gamma I k divided by 1 minus gamma high k. Do you know that if this guy represents gamma ik that is less or equal to, can somebody tell me what is 1 minus that? Mathematically speaking, what is 1 minus that? Because that's what you're saying here. What is 1 minus that? What is he saying? 1 minus that would be probability of what? Extra credit. If gamma ik is probability of yi less or equal to k, and if you take a look at the denominator here, 1 minus gamma ik, can somebody tell me 1 minus gamma ik will be what? Go ahead. Yeah, the probability of complement in mathematical, here is less or equal to, what would that one going to be? Go ahead. Greater than. Yeah, 2 of you send me a message for extra credit. Thank you for sharing. Okay, greater than will now be. So which means if I want to base on this example, this is going to be the log of somebody, an individual I work in a position not higher than managerial divided by work in a position higher than managerial. Does that make sense? That is just, and that is going to be equated, okay, to the systematic part. Can you see the systematic part? And from the systematic part, we're also going to have a way to estimate the gamma ik here. Okay, so take a look at that. Okay, now we can also talk about the ratio of the odds. The ratio of the odds. Okay, the ratio of the odds. Take a look at this guy. Odds for category K for individual high and odd for category K for a different individual. Okay? Odd for two different individuals. The ratio of odd for two different individuals. That's what we mean. Okay? And that is actually called odds ratio. Odd, not odd ratio. Odd, like plural. Look at that. Because this is a odd on itself. This is another odd. Then we're having the odds ratio now. Okay? Don't forget, like I said, okay, this is actually being used in a situation where categories are not expected to be the same. Now I'm going to walk you through an example of this. Okay. But let me tell you this. It is not appropriate for this data set. I'm going to say that again. It is not an appropriate for this data set. For this data set, the appropriate model should be multinomial, because I'm not going to say independent is greater than Democrat, or whatever party is greater than the other one. I'm not going to say that. Okay. So here, this is actually for, you know, um, maybe for practice. Let's see how the code of the logic proportional, the order we talk about, how it works. Now, you need to load a mass package and take a look at this. POLR. POLR. You can see this is different from multinom. Now, if we assume that we're still talking about the same data set that we used the other time, let's see how this look like. I need you to pay attention now. What do you see? You know, ever since we've been working on generalized linear model, it has been a Z value. What do you see? T. Can you see T value? Okay. That is one thing that you actually going to notice. But let me tell you this. If you look at the way it's going to report, okay, it's actually going to compare one at a time. You can see Democrats against independent, independent against Republican. Now, it's doing that in an ordering way. Take a look at this. When the four of us look at Democrat with respect to the independent, now the next is independent with respect to the Republican. And here you can see the values, the estimate, the standard. This actually came out like a regular linear regression platform. Okay. And of course, the intercept is actually now. Now, if you let me say this. Let me say this. The coefficient is this. Oh, sorry. Which is going to be for income only. Okay, that is the coefficient. Why the intercept? These are the intercept. These two are intercepts. The first one is the coefficient associated with the income. Then the other two will be intercept. Now, how do we make an interpretation here? I'm actually going to walk you through that. Now, because we're talking about ordering, I need you to pay attention. For instance, if I want to talk about the probability of y less or equal to 1, where the 1 is Democrat, I'll first number them. Oh, okay, Democrat 1, Independent 2, Republican 3. And I want to find what is the probability. Now, this guy means probability that that person is being classified as Democrat. And you know, uh, in that regard, we're trying to say the probability of y equal to 1 is more or less y less or equal to 1. Y less or equal to 1 equal to 1. We believe that there's no 0. Does that make sense? Because less than 1, if it is equal to 1, then we don't want 0, we don't want negative. Okay. And this is going to be the model. B01 minus minus B1 income. And where is the minus coming from? Please pay attention. Where is the minus coming from? Okay, is the minus coming? You can see I've not even indicated B1 and that, but we have a minus already. Place the minus come from the model naturally. Can you see that? Equation 9. Can you see equation 9? The intercept minus, not plus. Okay, the minus come from the model naturally, and that is why you see this guy here. So if you can just read the intercept, you can read the income right here. Okay, now if this is the first one is this of being Democrat is 0, then I want to find log of gamma 1 divided by 1 minus gamma 1. I need you to pay attention. If gamma 1 represents the probability of being Democrat, then the denominator is actually going to be it could be any other party. And that is why I said the probability of being either an independent or Republican. Please pay attention. That is how I'm going to interpret 1 minus gamma 1. The moment you settle for gamma 1, 1 minus the gamma, if it is gamma 2, okay, then it's going to be 1 minus gamma 2 divided by 1 minus gamma 2. Maybe I'm focusing on independent, the gamma 2, then the other one is going to be neither Democrat or the other one. Okay, so take a look at that. Now, if you take a look at, please pay attention. There's something I want to do now. I want us to have a sense of interpreting a change in income. But to do that, let us assume that our income is S. And what if there's an increase, a unit increase in income? Now, you know what I'm trying to do here? What I'm trying to do here is I still want to find that, but when income increases by 1 and when income remain the same, X. When I subtract that, of course, if this guy here, please pay attention. If this guy here represent B0 or B01 minus B1 X, right? Then this guy here is going to be B01 minus B1 in parentheses X plus 1. Does that make sense? In parentheses X plus 1. So if I subtract them, okay, and at the end of the day, what we're going to have, oh my God, do you know when we did this to logistic regression the other time, what we got was a beta 1. But when we do it now, it was a negative beta 1 here. Why negative beta 1? Because there's a negative that comes naturally with this module. Is there any question here? There's a negative that comes naturally. Now you can see this gives a negative beta 1. So, and if you mathematically speaking, if you actually, mathematically speaking, if you take a look at this, okay, the log of that, I can rewrite that as, okay, now I really want you to see everything so that you will appreciate what I'm talking about. Give me 1 second. Okay, so take a look at that. Yeah. You see that? The log of this minus log of this, I can rewrite as log of that, of log of this divided by that, and that give me negative beta 1. Oh my God. If I have a negative beta 1, if I want to make any interpretation, I still need to exponentiate. So what I'm going to be exponentiating is going to be negative beta 1. Does that make sense? That's going to be that. And mathematically speaking, exponential raised to power negative beta 1 is the same as 1 over exponential raised to power beta 1. This exponential raised power this is the same as this. This is what we normally call odd ratio, right? But 1 divided by that in the case of what we're doing now, which is the reason why we're doing this. Look at that. 1 over R or R. Can you see that? So this is going to read the odds of being a Democrat if income is X plus 1. So the odds of being a Democrat if income is S. Okay? So take a look at that. Now, when income equal to 0, you have the model to be that. We did it the other time. When income equal to 0, the probability to be Democrat when income equal to 0, when you plug that in, is the same thing as probability of Y less or equal to 1. But when income equal to 0, being an independent, okay, to be an independent or a Democrat, which means the probability of Y less or equal to 2 giving Y less or equal to 2 giving income equal to 0. If you take a look at what I have here, it's going to be that. And by the time you keep moving, okay, mathematically, that is going to be that, when you look at that. And of course, this is the interpretation. When you exponentiate 0.013 that we got the other time. If you go back here, the income, when you exponentiate that, okay? But when you exponentiate that, okay, 1 second. Okay, let me see. Okay, so when you exponentiate that, you see what we have is there is the interpretation. And of course, I said it is 1.0132 times more likely to be independent or Republican rather than a Democrat when the income increases of 1. That is how to interpret the slope. Okay, this is the logic aspect. Okay, the intercept correspond to that. When the income is 0, the predicted probability is that. This is how to use that in R. And why that being independent, that's how to do that. Okay, so these are the code. So like I said, now I'm actually going to say this. Midterm 2 questions will revolve around what we did up to this moment. Okay, after midterm 1 up to this moment. So I'm going to release a practice question over the weekend for that. Is there any question before I go on all of this, even though I think I'm 1 minute late? Sorry about that. So, any question on that? I provided a code here. Okay, I provided a code. If you're wondering where 0.209 is coming from, okay, you see that 0.209 is coming from, that is the intercept side, and that's compare Democrat and independent. Another intercept compare independent and Republican. And that is exactly what you're seeing here. That is where the values that we're using here come from. Okay? Which means we're analyzing the intercept now, the intercepts. Okay? So look at that. And of course, why that of being an independent is this minus that. You see that? The 2 minus that, and we actually give that, which is the probability of being an independent when income, which means the probability of being an independent when income is 0 is when you subtract the logic of 1.29 or 0.209 from 1.292. And where is the 1.292 coming from? So both is 0.209 and 1.292. They should be intercepts in the model. Can you see them? They are intercepting the model. Okay, so they need to be subtracted. Okay, the logic of that need to be subtracted. Okay, the logic of that need to be subtracted to get for independence, because the 2 has independence in them. So okay, so that's why I'm going to stop today. Make sure you all stay safe and have a lovely day. Bye for now, everyone.